Last year in autumn, I was on Google Developer Conference, and the machine learning talk I attended there focused pretty much on two topics. The first one was the website tensorflow.playground.org, and essentially what it is, it's just a toy that allows you to get some intuition about how neural networks are operating. The second thing they showed is Google Vision, and Google Vision is an API provided by Google. You can upload there your picture, and Google, using their internal neural network, which is called Google Brain, will categorize this picture accordingly. So in this particular case, I've uploaded the picture. Google Brain correctly identified this as Eiffel Tower. It actually even is able to tell us that this is the Eiffel Tower that is located next to the Strip in Las Vegas. The one thing that I was missing during this talk, though, is the explanation how to get from this thing to this thing. And the thing I want to talk to you about today is how we back at AirHelp are doing this transition from the very basic first model into the actual product. So let me click present. Let me introduce myself. My name is Michał Jakóbczyk. I'm the Director of Data Science at AirHelp. Before AirHelp, I worked in several other companies, including over 8 years at Google. And the company I work right now, it's like 500 people still. We're a startup with 100 people in IT department. And one of the things we do is quite a little bit of data science and data analysis. So let's start our journey. And our journey starts, in this case, with a little bit over 3 hours delay. According to European Union regulation EC261, if your flight is over 3 hours delayed, you're entitled to compensation. And obviously, you can go to the airline and ask them for compensation by yourself directly, and sometimes they do pay. Otherwise, you can use one of the companies like mine that will contact the airline and get the compensation on your behalf. One of the things you have to provide us so we can represent you is actually a paper. This is called assignment form that grants us rights to speak on your behalf. And you have to make your signature to make this document valid. So those are the examples of the correct signatures. And here's a fun fact. The airline doesn't know how your real signature looks like. So the only thing they are checking is whether this thing that we've sent them looks reasonable, looks like a valid signature. Because sometimes our customers are sending us things that don't look that much valid. And one of the things we do in our process, we actually have agents, so customer service people, who are looking at every document, every assignment form sent to us, and they're checking whether the signature is correct one, or if something went really, really wrong there. And the project I will tell you about today is actually a model that is trying to assess exactly this. Instead of, so whether the signature looks valid or whether the signature should be corrected by our customer, because we really don't want to send those to the airlines. If you think about this from machine learning perspective, this is actually supervised learning, a binary classification problem. Short recap, binary classification means the model is supposed to answer one simple question. Is this a correct signature? Yes or no? Is this a picture of a cat? Yes or no? Supervised learning is description of a method of building such a model. So in this case, you have several thousand of labeled training data. So for example, you have several thousands of signatures, and each of those signatures has a label, correct, incorrect. Or several thousand of pictures, and each of them has a label, cat, not a cat. Now, typically, the state-of-the-art solution for visual analysis nowadays are convolutional neural networks, and for obvious reasons, this is what we use. The convolutional neural network is the enhancement of classical neural network. What you can see here is actually a typical fully connected neural network. So you have some input nodes, and in case of pictures, usually a pixel is assigned to a single input node. You have output nodes, so in case of binary classification, this node would be representing cat answer. This node would be representing not a cat answer. And then you have one or more hidden layers. Now, the trick is, in this case, you can see that this is so-called fully connected neural network. So every neuron from the previous layer is connected to all the neurons from the next layer. It makes it very difficult for the neural network to create a model if we have huge pictures, like few thousands of those input nodes, just because then the neural network has to somehow decide about the values and the weights, the parameters, in other ways, of each of those connections. Convolutional neural networks work in a slightly different way, so they actually change so-called the architecture of neural networks, so how many connections we have and how they're organized. And they come from the research done in the 50s actually on visual cortex. So it turns out that as we look at things, we're not looking at the whole picture at once. Our neurons that are responsible for visual perception are actually connected into local receptive fields, so-called, meaning that we are not looking at the whole picture. Part of our brain is looking just at a part of a picture. So in a way, it simplifies the work and subsequently, after this discovery, when it was transferred into the computer science, the practical approach was just to limit the number of connections between the input nodes and the subsequent layers. So just to give you some intuition, I don't want to go into CNN details here. Imagine that you have a picture, and on a picture you put a white paper and you make a hole in it. And then you are actually trying to identify what's on a picture just by looking through this hole and shifting this piece of paper. And this is essentially what CNNs are doing. They're doing a little bit more later, but I think this intuition is good for the beginning. So how to build such a network? Well, you start with fetching the data. And as I told you, in our case, what we do have is 2 years of work of our agents that were manually labeling the data. So it all comes down just to going to a database, sending a SQL query, and hey, here you've got the data. Once you have the data, you build a model. We used Keras, which is an API layer on top of TensorFlow. And actually what you can see here is a full definition of a model with even with a method that's training it. And you should get used to the fact that your initial models, including fetching the data, including building and training the model, including even calculating the final metrics, some visualizations, it will be like 200 to 300 lines of code nowadays. It won't be much. Now, once you have this, you train the model, you draw some metrics, and here comes the question. Is this model good enough? Should we put it into production? Should we work more on this model? How much more? Now, to address this question, we need to take actually 2 steps back. And we need to start looking at our business. And in our case, it means drawing a chart showing how often our customers over time are sending us incorrect signatures, and how often our agents are failing to catch such miswritten signature. And this basically gives you 2 information. The first thing you get is by knowing how often this type of error occurs in general, you can assess the cost of error. The second thing, the quality of the work of our agents, give you a baseline for your model. I mean, the rule of thumb is your model should be as good as a human being that you're trying, ugly speaking, to substitute. Because if it's worse than talking to stakeholders, trying to convince them to deploy your model will be really, really, really hard. One additional thing we're learning when we are drawing such charts is actually that our data set is highly unbalanced. Majority of our customers are giving us correct signature, which is not surprising, by the way, because if you already put a lot of effort into sending a request for compensation, you won't be goofing around with a signature. So from the technical terms, it means you actually have to oversample the incorrect examples. Now, these charts, and by the way, I'm just showing 2 sample charts. You usually draw a lot more of them. They're telling us basically that our model is nowhere near the quality we would like to have. So there's a famous quote you probably heard of: garbage in, garbage out. It basically means that if you're feeding your model with training data that make no sense, you should never expect to get a model that is of a high quality. So how do you check? And this is the first thing we usually do. We check if a model is not super from the beginning. We check what data we have. How do you do this? Well, here the magic comes. You actually look at the data. And in this case, you can see we have some incorrectly classified, examples. And they're blurred because they are the real signatures. But you can see here that this looks like a valid signature. This one actually as well. And this one looks solid. So what happened? Well, we checked that the labels on those signatures were actually marked as incorrect. And to understand why, you have to go to business. You go to business, you talk to the people, and you find out that in your process, you have day shift and night shift. And night shift people are less motivated, far less trained, and, well, honestly speaking, they do worse job. So, and also you learn that there's this one individual who doesn't work with us anymore, and he was doing a really crappy job. So you do exclude those type of data from your training set, and testing as well, by the way. Once you do it, you learn that your data starts looking better. Usually you do repeat this process a few times until you're satisfied with the quality of your data. And after this phase, you actually can get to model optimization. And here's another thing. You usually don't do too much research when you're optimizing a model. I mean, you buy a good book, you open a very good tutorial, you ask some people around maybe who have more experience, and you try a few different experiments. It can be 5 experiments, it can be 200 experiments. But at the end of the day, this is a guess. Hopefully it's an educated guess. And this all comes down usually to things like, okay, let's pre-process the features. Let's get more training data. Let's add some regularization. Let's play with hyperparameters. So the one essential thing for us when we're doing 50 or 100 of such experiments is actually not to get lost and what we've done, what we haven't done, what worked, what didn't. To get there, we actually have a very simple method, namely we have a process and documentation that we follow for every experiment we do. So, to going one by one, you have a name of your experiment, you have a description, meaning you have some hypothesis that you're testing. If you don't have a hypothesis, well, don't start playing. You have a GitHub branch, and I really want to stress this one out, because for every experiment you do, you want to store both the code you use and the data used. So in a week time, in a month time, in half a year time, when you go back to it, you can easily reproduce the whole experiment. Because sometimes, even if the experiment fails today, in a week or 2 weeks or 3 months, you're getting to a point where this experiment actually starts making sense. The next thing are results, and you should always have some small subset of metrics that you use for judgment of every experiment, and this subset of metrics regarding one project and one series of experiments should stay the same. So it's an easy way to decide whether you want to reject the experiment or let it stay. I also have here 2 data sets, and this is something that helps us. I mean, we have small testing set that's very quick, and it's good for prototyping. Because again, for reality, I told you to store every experiment, code for every experiment. But in reality, what you will discover is that for a single experiment, you're trying a few different parameters, few different flavors, and so on. So even for a one simple single experiment that takes a few hours, you probably try to train your model, test your model a few dozen of times, a few hundred of times. Not mentioning the experiments that last 2 or 3 weeks. And also the large data set that we're using to finally check whether we should accept the experiment or not. Now the thing is, this data should be also kept in a safe place, and probably if you are working on the model in a team, so there are a few people optimizing it. All of your colleagues should have the same set. Then you add all the other metrics you wish, just if you want to dig deeper into what was happening, do some in-depth analysis and so on. And you repeat those two previous steps, I mean, training, data augmentation, and model optimization until you're happy. When you're happy, then pretty much you can start getting ready to putting your model into production, talking to your product and talking to the stakeholders about the migration steps. I mean, there is a large fear of change in organizations when you're introducing new solution, especially AI solutions. There's some magic behind it. People are not trusting whether it won't spoil the results and so on. So in practice, you usually want to roll it out gradually, and for sure you want to agree with your customers or stakeholders, especially as if this is the enterprise type of AI, not B2C type of AI, that they know what's happening, they have a way to give you feedback. Because the difference between the regular projects when you're building a website or building some application and the machine learning projects is that you usually have only just one chance to get it right. Because if people you're trying to convince to use your model will start using it and they learn that it's generating crappy results, I mean, they use it once, they won't try it again. So you have to keep this in mind. You roll out into production. The one important thing there is to make sure that you have, as I was mentioning, storing all the experiments. Make sure you also have all the scripts or code that is allowing you to redo the model at any time, rebuild the model, also well documented and stored. Because even if you're not rebuilding your model every week or every month, trust me, in a half a year, you will learn that you have to work on this model again because the environment has changed. Speaking of which, the one final thing that you should do is to make sure that you're monitoring what's happening to your model. So obviously, you have to have some business impact metrics. You have to understand the error rate that is happening there. But you also want, if possible, monitor the input features to the model if their quality is not degrading. By the way, this type of chart is something we start with. I mean, if we're starting a model, if we're starting a project and we cannot come up with a solid metrics that we would be tracking once we finalize the project, then we shouldn't even start the project. I mean, if you're building something that you don't know how to measure if it brings value or how it works, why even work on it? Okay, I actually made it quicker than I thought, so I should speak slower, sorry. This is all I had to say today. Thank you very much for listening. If you have any question, feel free to shoot. And also, this is the way we do work back at AirHelp. If you disagree with this way, I mean, I encourage you to argue with me. I really like arguing. Thank you very much.
Thank you, Michał. It was a great talk. Any questions, guys? Here we have.
What was the results of your project finally? What was the success ratio?
It's in production. So it's a good question. The answer is not that simple, because this is actually not the most important project we run. This is something that was built by one of my junior developers over summer last year. It took like a month and a half. And this is something I would call an enable project. So we have internal stakeholders and we are changing their process, we are augmenting their process with different models, different bots. One of the things they were afraid of is that, hey, this is this signature thingy, and even if you automatize everything else, there's still need for people to look at the signatures. So we just wanted to show them that we can build a model that is actually equally good as a human being in tracking the incorrect signatures. So it had a reasonable level of similar level of errors.
Thank you.
Okay.
How regularly you feed the model? You said you can review it in 6 months, but since there are people still building data, evaluating the signatures, can it be automated, and what infrastructure do you recommend for that?
It could. The question is if you want it.
Yeah.
So here's the thing. In our case, this is why we build those dashboards, because I don't want to build the infrastructure for automatically retraining the model, because then I will have to have some physical person making a decision whether to allow the model on production or not. I mean, we're not. I don't know a case based on my 15 years of different companies where there was an engine that was automatically training a model, validating with training data, and just pushing the production without any knowledge and human intervention.
You can evaluate it with rock curve, for example.
Pardon?
Can rock curves and some metrics be used to compare the previous model?
They could.
This is not without.
Mm-hmm.
Yeah.
They could. The problem is that there's usually not direct transition between machine learning metrics and the business metrics. So let me give you a quick example. I put this picture on purpose, actually. This one, this leaf thingy. This is something you really don't want to send to your business partners. And if you just take the machine learning metrics, what you will get is the high accuracy, high precision, high F1, beautiful rock curve, AUC, whatever. But you still get a lot of mess if you send this to a business partner. So that's why you usually want to be on a safe side regarding accepting your new model and have some human evaluation as well. And it also depends on the use case. I mean, I'll come back to this slide here. You do want to track business value of your project. So when the coverage or when the recall or precision drops below a certain level, this is a moment where you really want to retrain the model. If you can see, and in our case, we know that for over half a year, a model was working fine and was slowly degrading. So there's no point in putting effort into retraining it if we have other more prioritized projects. That's as simple as it is.
Okay, thank you. It was a really nice talk.
Thank you.
I have two questions. First one about repo. What you said, you create a new repo per project. The question is, how many branches do you have usually per repo? It's like 100 or less. And do you have any strategy about naming of these branches?
Tens tens of branches usually. And again, in practice, if you have because I told you, okay, put into a branch every single experiment. The reality is, if you have an experiment that completely doesn't make sense, you can forget about this. That's why it's not hundreds, it's tens. I don't have any specific strategy. I mean, you pick a convention and you stick to it. So, sorry, I'm not good at coming out with names, so I don't have a golden bullet here.
And second question about, so for example, here you have imbalanced data set. Why you use ROC curve? Because in this case, your missed false positive.
And you're absolutely right. I use ROC curve because this is a presentation I'm showing after a year. And I should use precision versus recall, obviously. That's a very good point.
Thank you.
Any other questions? No, they were just okay. All right then. Thank you very much, Michał, for the talk. It was really interesting. Perfect.